All right, so we started 4-4 with the introduction to ln, right, and e. E is the natural base. Ln is the log of the natural base. So ln is the same thing as log base e, okay? And we talked about that if I do ln of e, because that's log base e, right, that actually would become 1, cancel through it, and you can actually keep the exponent. So there's a couple different ways to look at how this happens, but basically the shortcut is just canceling through them. But if I wanted to put this first one, let's say I wanted to put it into, expand it. So what happens to an exponent when I expand?
Negative 10t goes in the front.
Good. Negative 10t would go in the front. This would be ln of e. And ln is the same thing as log base e. And any log with the same base as the large number would just be 1. So this would cancel through, and I'd get negative 10t times 1, which is just negative 10t. So that's the longer way around it, right? But hopefully you know that there's a shortcut. The shortcut is if you see ln of e, you cancel through it, and you keep the exponent as your simplified answer. So then 2, now you've got e to the 0.25 of ln of t. So my exponent has a log in it, okay? So if I wanted to take this and do the opposite, that's being multiplied times the front. So that 0.25 should become the exponent on the ln of t. This would be e to the ln t raised to the power of 0.25. And then just like ln of e would cancel, e to the ln cancels, giving you just the exponent. So this would be t to the 0.25. So ln of e is going to cancel, leave you the exponent. E to the ln cancel and leave you with the exponent. But you have to move that 0.25 first, because I need the ln and the e to be next to each other. Okay, so now ln of e, we know I would cancel through this and leave the exponent of x. And then this would be negative 1 times x, which is just negative x. T to the 0.25. So the 0.25 has to become the exponent on the t. Okay, number 4, this time, ln of e can cancel. All right, so ln of e cancels through, giving you just the exponent, and then I've got 2 times x to the second. Yep.
How do you know if it, like, if it's going to be 2x to the second or like 2x third?
You mean if you move it first?
Yeah.
So if you move it first, it ends up being the same because it would be like, so if I move it first to the exponent, e to the x squared raised to the power of 2, this would be ln of e to the, you'd multiply that, right? So you're raising a power to the power, which is x to the 4th. And then you can cancel it out and keep it as x to the 4th. So it depends on the order that you do it in. Whereas the other ones, it doesn't, there's none on the front, so it doesn't matter what order you do it in. Like for that first one, there was nothing on the front.
So is the answer 4?
So the answer, actually, yeah, the answer should be x to the 4th. So you need to move it first. Whereas 3, it doesn't matter, right? Because it's the constant is the same. So 4, it does matter. Thank you. You need to move the exponent first, and then ln of e. So ln's got to be by itself before you can use that shortcut. Ian?
You said ln was log base e?
Correct. Yep, so they're interchangeable. You can either use a shortcut or you can rewrite it as log base e. Okay, so we're going to finish the note started on Friday. It's 4-6. We left off with the graphs of the natural logs. So we're going to get a little bit more into the graphs of logs, exponentials, and stuff tomorrow. We're going to start using some transformations like the shifts right and left, up and down, vertical compression, vertical stretch, all that stuff. But this is just the basics. So we talked about the basis of e to the x. If I was graphing e to the x, it would be an exponential function, like this one here. Similar to as though if it was 3 to the x, right? Because e is an approximation, but approximately 2.7. So if I was graphing e to the x, my line would look like that blue one, which I just wrote over in purple. Because these are inverses, so natural log is the inverse of the natural base, it would be just like a log. So it's going to appear to be like that red line. It would be very similar to log base 3. So the domain is 0, or greater than 0, can't be 0, greater than 0. And the range is all real numbers. On the exponential function, it was the reverse. On e to the x, the domain was all real numbers. And the range was y is greater than 0. So remember they're inverses, which means you switch the x and the y values. Ian?
Can you go over that first bullet again? The definition.
So it's not really the definition, it's just saying that it's the inverse of e to the x. So if I was to graph a log base e and then switch all of my points, I would get e to the x, or vice versa, which is probably easier to do it the other way around. Like, remember we graphed the other day, if it said f of x equals e to the x, and I set up my t-chart, -2, -1, 0, 1, and 2, and I got all these points on the bottom, right? Whatever I got here, 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 here. And then I asked you to find the graph of ln of x. It's the inverse to e to the x. So I would take all my x and y values and simply flip them. So, like I said, we're going to go a little bit more into depth on these graphs and what they look like and how to shift them left and right and make them taller, like vertically stretched or vertically shrunk. That's in the next section. For right now, you just want to understand basically what the parent function would look like. So the e to the x is going to be a growth function, exponential, so it's increasing as you move to the right. And the ln is going to be like a log function, which is going to be more like that little red line there that's on the bottom.
But what is the x doing on the ln there? Is it like multiplying it?
You'd be finding the ln of that number. So if you used your calculator, you would actually do ln of -2, ln of -1, ln of 0, like that. All right, and then the last thing in this section is continuous compounding interest. So this is the PERT formula, and the PERT formula occurs, or you use it, when you're finding how much interest is being earned when your investment is being earned compounding, meaning I have $1,000 in a bank account and it's being incurred 3.5%, but it's being compounded, which means, let's say it's just earned 5%. Now in another second, it's another 5%, and then it keeps going, so the growth is bigger on PERT than simple interest because it's starting to earn money on the new balance. So if I put in $100, let's say, and I'm earning 5% compounded continuously. That means at the end of that first second, even, it's faster than a second, but after that time period, it just went up 5%. So my 100 just went to 105. And then instead of it being only compounded once over that whole year, it's continuously happening. So at the next second, my 105 is now getting multiplied by 5%. And then the increase and the increase. So compounded interest is the fastest growth of money. So it's the most bang for your buck if you're going to be compounded, which it sucks on credit cards because this actually happens. Instead of it being like an annual, they can do an annual APR where you have a balance and they're only going to charge you once that year, or monthly where they're only going to charge you once. And then they have compounded continuously, which means they keep hitting that money. And every time it grows, they keep doing a new percentage of that. So this formula, I call it PERT. It's P, which is the principal rate, the money that you're putting in the account, times E, which is your variable, right? E is like 2.7. So E to the RT. R is the rate, and it has to be in decimal. So you're going to take it from percent and put it into decimal. Times T, which is how many years it's in that account, okay? And then you let your calculator do the work for these. That's the good news. All right, so it says, what's the total amount for an investment of $500 invested at 5.25% for 30 years, compounded continuously? So my overall investment is P times E to the RT. The P is the principal amount, so it would be 500 times E. All right, so then that R should be this percent converted to decimal. So 5.25% is what as a decimal? 0.0525. Got to move my decimal 2 places, right? Times T. How many years is it in there? 40. So then I let the calculator do that work for me. Okay, you got to make sure that both the 0.0525 and the T, which is 40, are in your exponent, so it's not multiplying. So you would do 500 times E to the 0.0525 times 40. And again, make sure that 40 is in the exponent. You should get $4,083.08. This one that you looked at, $500, you started out with a little bit more money, but you had it in there for 40 years, and the 5% was a little bit bigger, so there should have been a bigger jump, okay? So hopefully you can kind of do some comparison there. All right, so that wraps up 4.6. Thank you, 4.6. So we'll use the rest of the time. I'm going to do what I did last time. I'll post the extra worksheet on there too, okay, so that you make sure that you're good and solid on 4.6. And then tomorrow we'll do 4.7, which is the last section of the chapter test Friday, okay? All right, so my formula again is A equals PERT. A stands for the balance of the account after the time that's given. So the principal interest is the principal investment is $100. E to the, what's my exponent? What is 3.5% in decimal form? 0.035. Number of years is 8. And then I would do 100 times E to the 0.035 times 8. And it's $132.31. So when you compare, hopefully, common sense can help you along the way here, too. 3% is not a lot of money, and it was in there for 8 years. So you don't expect a huge growth, okay? Whereas the last